So today I wanted to cover the oxidation part of chapter 10. So we had started to talk about oxidation of alcohols. And remember, at least in organic chemistry, when we're talking about oxidation, what we're really kind of saying behind the scenes is adding bonds to oxygen. That isn't to say that we're dismissing any of the other definitions of oxidation, and certainly you could go through and look at oxidation charges or oxidation states or oxidation numbers, whichever term you want to use there, and we would come to the same conclusion. But really, at least in the undergraduate two-semester organic course, when we're talking about oxidations, we're really looking at how we can add bonds to an oxygen, and specifically from carbon to oxygen. And so, we have dealt in this course a lot with alcohols, right? And in this section, at least, what we're going to do is take those alcohols and transform them into some carbonyl, right? And so here we have one bond from carbon to oxygen, right? And here we have two bonds from carbon to oxygen, right? Here we have our 1 sigma, here we have our 1 sigma and 1 pi bond. You can see that we're adding bonds to oxygen as we go through this. So that's all we're talking about. Now, practically speaking, we're going to limit ourselves, at least in chapter 10 here, to only making a certain set of these carbonyl functional groups. Remember, when I'm talking about carbonyls, right, I'm looking at that part of the functional group there, a C double bond O. So we're going to stick from aldehydes. Whoops, I misspelled it. Aldehydes, ketones, and we will even talk about carboxylic acids. Okay, so we're kind of going to be living within these three carbonyl groups here: aldehydes, ketones, and carboxylic acids. Now the problem is, or the issue that we're going to have to concern ourselves with is, if we want to specifically make an aldehyde, right? If we want to specifically make an aldehyde, we're going to have to set up a certain condition for that. Okay, we're going to have to set up a certain condition for that. Ketones and carboxylic acids, they're going to have slightly different reaction conditions, and I'll point that out as soon as we get there. But really what we want to say is aldehydes and carboxylic acids, we're going to have to really pay attention to those. Ketones are going to be pretty easy to make, right? And I'll talk about why in just a minute. But ketones are going to be the easiest ones to make, and then aldehydes and carboxylic acids we're going to have to pay a little bit more attention to, specifically with the reaction conditions. The other point I want to say is this is not an exhaustive list that we're going to be going through at this point. We're really only going to be dealing with about 4 to 5 reactions. In reality, there are probably at this point, hundreds of reactions to do these oxidations. So I'm just pulling the reactions out of the book that I want you guys to focus on, just because you will see these specific reactions used quite a bit, and they are going to be extremely useful for us in terms of setting up some of these synthesis problems. So we're going to focus on all 3 of these and how to make them, the aldehydes, ketones, and carboxylic acids. And we're going to spend quite a bit of time just kind of explaining how to tell when you're going to make these specific reactions. Okay, so let's start with the simplest then. Let's discuss ketones. Let's discuss ketones. Now, ketones, we are going to need a secondary alcohol, and if we have a secondary alcohol, the max we can do with it right now, is turn it into a ketone. Right, and here's what I mean, right? If we have our simplest of secondary alcohols, right? If I add a bond to oxygen to it, right? If I add a bond to oxygen, that's it. Oops, let me just make that a little bit better there. Right, if I add a bond to oxygen, that's it, right? If I zoom in on this a little bit, right, just clear this up, let's turn that hydrogen red, right, and that hydrogen red here, that understood hydrogen, you'll notice that I have to remove those two hydrogens along the way. So another way of kind of looking at how I can deal with oxidations is by how many hydrogens I can remove. We are not going to be dealing with carbon-carbon bond cleavage, right? So we're not going to cut any carbon-carbon bonds in this part of the chapter, okay? Let me back up here for just a second. There's going to be one reaction to deal with, but it's going to be very unique, all right? So when we're dealing with how to tell where you can go with our oxidation, secondary alcohols, we can remove those two hydrogens without cutting any carbon-carbon bonds. The max we can do is simply turn it into a ketone, right? I can't add any more bonds to oxygen to that carbonyl carbon because then we would over-octet it. So how do we do this? Well, there's 4 ways that we will learn at least. So if we start from our alcohol, okay, let's pick some different colors. I will use something called chromic acid, okay, H2CrO4. Another way you might see this is if you have some kind of chromium salt. So you might have something like CrO3 in sulfuric acid and some water around. Okay, so some kind of setup where you have chromic acid. Another way you might end up seeing it is if you have here sodium at Na2CrO4, and then we add some sulfuric, right? If we have that, so sodium chromate with some sulfuric acid, you could even see Na2Cr2O7, right, and sulfuric acid. So sodium dichromate and sulfuric acid. So there's actually a lot of different ways to kind of set up this reaction. There's 2 key points that I want to make with this. All this, right, any of these stuff, so any of these things here, right now, this is the only reaction that we're going to know that has chromium in it, right, that's going to use chromium to do something. So if we see any of these chromium salts, these chromium oxide salts with some acid around, it's all pushing towards making this chromic acid. When you mix any of these things together, you're going to end up forming this, right? So one way or another, we're getting this chromic acid here. A key important point to note also, water, right? We're going to have water around in all of these reactions. It's not explicitly stated sometimes, but take my word for it, there's going to be water around, okay? So any of these types of chromium-based reactions, we're leaning towards making chromic acid, and we have water around. Now for me at least, I usually end up putting water in there just as a reminder for me, and that'll be important in just a minute, okay? But it's important to remember any chromium salt right now is chromic acid, right? It's going to form chromic acid at least as long as we have these other acids around, and then we're going to have water around, okay? So let me just clean this up so we can explain what happens. Although you guys already know what happens because it's written right above. If we have chromic acid around, we are going to form our ketone. Okay. Ta-da! Shocking, surprising, amazing. Okay. Next thing we can have around is something called PCC. Right? PCC. Okay, so PCC stands for Pyridinium Chlorochromate, right? So let's just draw that out real quick. So we've got a pyridinium, which is the protonated form of pyridine. So pyridinium, right? So N has a positive charge. Chlorochromate. So we have something that looks like this. Okay, so pyridinium chlorochromate. Pyridinium chlorochromate. chromate. Okay, so what does this do? Well, PCC is going to be a very useful reaction for us in just a minute. Again, we'll explain why. Okay, but right now, what do we notice? Well, we've got another chromium in there. And this is going to be kind of one of these repeating patterns that you guys will see all along in organic chemistry. Okay, so chromium is going to have a specific role in a lot of different reactions, but most of the time, at least what we're going to see chromium used for is these types of oxidation reactions. Okay, so if you're on your MCATs or any kind of exam that you guys need to take with organic chemistry, and you're kind of drawing a blank, think that chromium is going to do oxidation, right? That's usually going to be a pretty good guess of what's going to happen with any type of chromium salt. Okay, but here we go. PCC, not too much else I need to say about this. It is going to oxidize a secondary alcohol to a ketone. Okay. All right, let's bring in another reaction here. Let's do this one in purple. Okay, in this case we'll use DMP. DMP. Now DMP stands for, I'll just write this out, Des Martin. Just referring to the people who, first applied this here, the scientists. Des Martin, PER, per iodine. Pyridine. Okay. Okay, so PERIODIN. Whoops. PERIODINANE. So Des Martin per iodinane. Okay. Okay, now, as with all my classes, and I said before, I don't need you guys to remember names necessarily, although some of you guys, it might be a little bit easier to remember the names of stuff. Here's how this looks like. We got a nice old benzene ring there. That benzene ring is bound to an interesting looking 5-membered ring. Got an iodine in the middle of that ring bound to an oxygen. Over here we got a ketone ester there, right? Excuse me, a carbonyl ester. And then we've got a bunch of OACs. All right. Now remember, OAC is an acetate, right? So OAC, right? We got O like that, right? So we've seen acetate quite a bit, right? So shorthand for acetate. That's what the DMP reagent looks like, okay? Again, I don't need you guys to memorize that, but I just want to show it to you, and so it's not just a word salad or letter salad for you guys. There is actually a structure behind it there, okay? Now DMP, it's going to do the same thing as our other two, right? Same thing as chromic acid, same thing as PCC, same thing as DMP with a secondary alcohol. It's going to take it into a ketone. And there is one last reagent that we need to talk about. We'll do it in black here. Okay. Actually, I'm going to have to draw myself a slightly bigger line here. I've got to do a little bit more writing. Okay. So we are going to use something called COCl2. Whoops, excuse me, COCl in parentheses 2. I'll draw that in just a second. Okay. We are going to need some DMSO. Okay. And then we're going to finish this up with a number 2 and add in some ET3N. Okay. So that is a mighty looking jumble of letters there. So let's start to kind of make some sense out of all this. So let me find some room here. I think I can fit it here. So COCl2. That is something called oxalyl chloride. So oxalyl chloride. Now, oxalyl chloride looks like this. We got carbon bound to carbon, double bond O, Cl, Cl. So this is belongs to a group of carbonyl compounds which I don't think we've seen it yet in the first semester of organic. Right? This is an acyl halide, ACYL halide. Now you will talk a lot about these when you get to the second semester because there's I believe like 2 chapters that you guys go through with carbonyl chemistry. And so you'll talk a lot about acyl halides, but this is a functional group which is in the list, but we haven't talked about it much in the first semester at all. So that is what COCl2 looks like, acyl halides. DMSO, we've seen this before as a polar aprotic solvent, right? As a polar aprotic solvent in our SN1, SN2, E1, E2 chapter. There's DMSO, dimethyl sulfoxide, so dimethyl sulfoxide, and ET3N, triethyl, so 1, 2, 3, so triethylamine, right? Triethylamine, there it is. I'm trying to separate this all out here so we can have all the notes on one. All right, so there's your part for a Swern oxidation, SWERN oxidation, Swern oxidation. Now, these are the 4 reactions which we're going to be dealing with for the oxidation part, at least. Okay, so we're going to see these 4 reactions over and over. I don't need you guys to know the mechanism for any of these. They are in the book or they're online. It is useful to kind of go through and look at it, and I will make the point that if you go look at these mechanisms, you will see that we see a lot of the same mechanistic steps at work behind the scenes, right? So the idea of Lewis acids and Lewis bases is very prevalent with how these particular reagents work. Okay. Anyway, there's our 4 reactions. This is what we can use to turn a secondary alcohol into a ketone. Okay, so now that we've dealt with secondary alcohols and making ketones, let's take a look at how we can make an aldehyde. Now it should be noticed that to make an aldehyde we have to have a primary alcohol. And we can only make an aldehyde from a primary alcohol. Aldehyde, okay. So if we take our simplest of primary alcohols, right, our buddy ethanol maybe there, okay, we will have 3 options to turn that into an aldehyde. So again, we can use PCC, okay. We can use our Swern oxidation. So remember our Swern oxidation has our oxalyl chloride, COCl2, some DMSO, and we finish that up with our triethylamine, okay, Swern oxidation, or we can use our DMP, our Des-Martin priodinane, DMP. And if we do that, we set up those conditions, ta-da, there it is, okay. Now you'll notice what's missing from this, right? What's missing from this is the chromic acid, right? We're missing our chromic acid, and there's a reason for that. Now if we decide to take our primary alcohol, okay, and we react that with chromic acid, let's see what color can I use here, red seems fine, right? If I use chromic acid or any of our setups to generate chromic acid, what we will do is end up forming a carboxylic acid. And you'll notice what the issue might be, right? So if, let's use, let's see, what color have I not used here? A light blue seems okay, right? We'll notice that in an aldehyde we've got that remaining hydrogen there. Right, we've got the remaining hydrogen. Remember, as we remove bonds from carbon to hydrogen and add bonds from carbon to oxygen, right, that's kind of the whole idea of oxidation. And it just so happens that chromium, right, at least the chromic acid there, is a very aggressive, let's call it an aggressive oxidant, right? It is going to completely chew apart those carbon-hydrogen bonds and replace them all with carbon-oxygen bonds. Okay, so our chromic acid at least is our option if we want to do a primary alcohol to a carboxylic acid, but we'll have to pick some of our softer, right, oxidants, right? So we'll call this softer, right? Call these softer oxidants, right? And we'll call these a hard oxidant, okay? Now we have to be careful. I'm just using, you'll notice I'm putting some quotes around this whole hard and soft because there is a couple of theories in chemistry that work on, this idea of hard and soft. So we just have to be careful about what we're talking about here, but at least for terminology at the moment, what we mean by softer oxidation is that it is selective, right? We can selectively stop at an aldehyde, whereas our harder oxidants go all the way from all the way from alcohol to carboxylic acid. So we'll notice there's a progression, right? We'll notice there's a progression. If I've got a primary alcohol, right? So at the bottom here, alcohol, right? A primary alcohol, we can take that into an aldehyde, and all the way up to a carboxylic acid. Okay. If we want to stop, sorry, I have no idea what I was trying to spell there. Jeez. Okay, if I was trying to stop at an aldehyde, I need to pick a soft oxidant to get there. Right? If I want to go from here all the way up to here, right, I'll need a hard oxidant to go there. If I have a secondary alcohol, right, ketone is all it is. We cannot make it to a carboxylic acid yet, okay? So for secondary alcohols, it doesn't really matter. We can pick either the hard or the soft. In tertiary alcohol, no reaction for oxidation, right? No reaction for oxidation again yet. Okay, so we kind of have a level that we have to pay attention to here, right? The easiest one, if I have a tertiary alcohol, not going to do anything for us in this chapter, okay? Tertiary alcohols, they will not react with our any of our oxidations, okay? Secondary is only going to go to ketone. We can pick whatever we want. And primary, we have to pay attention to, right? Because primary, if we want to stop at an aldehyde, we have to make sure we're picking the right thing, okay? Now there's one more reaction that I want to chat about, and it's going to be a little bit, let's say, of an interesting reagent here, and it's going to do something that we've seen before. But let me get a brand new slide here so that we have some space to talk about this. Okay, the last reaction that we want to talk about is something called periodic acid. Okay, periodic, not periodic necessarily, although it looks like that certainly. Periodic acid. HiO4, right? Periodic acid. Now again, this is going to act as an oxidant, okay? But it's going to be pretty unique. And here's what happens, okay? So let's say that I've got this compound here, a vicinal diol, If I drop in some HiO4, okay, what we're going to do is very similar to O's analysis. Or we're going to snip, we're going to slide, and we're going to slap, just like we did previously. Okay, so we're going to snip apart the bond between the two alcohols. We're going to slide those two pieces apart, and we're going to slap down a double bond. Okay, snip, slide, and slap down a double bond. So again, this is now only our second reaction, where we see, right, a carbon-carbon bond cleavage, right? So along with O's analysis, now we have another reagent that we can use if we want to cleave a carbon-carbon double bond. What else is useful about this is only really the second reaction that we've learned where we can use our vicinal diols, right? Our vicinal diols here. Right, we haven't learned too many reactions that we can do with vicinal diols specifically. Right, we've talked a lot about individual alcohols, but a vicinal diol, we've really only learned the periodic acid. And as a quick review, can you think of the other reaction that we've done with these? The other reaction that we've done with a vicinal diol looks something like this, right? Where we have sulfuric acid and we remove water along the way, right? So that's a pinnacle, right? A pinnacle reaction or pinnacle rearrangement. So a diol, right now we have two reaction options with that. The periodic acid, we can cleave those apart and have two carbonyls left over, or we can do a pinnacle rearrangement and end up with a carbonyl also. Okay, so take a look at your notes for the pinnacle rearrangement, right? You'll see the mechanism and everything in there. But that is the end of our oxidation portion, at least for chapter 10. I don't need you guys to know the mechanism for any of these, right? They're fairly complex and they're very specific, right? Although, as I mentioned before, you guys do know the individual steps, right? We have seen the individual steps. It just might be a little bit more challenging with some of these more complex transition metal-based reagents in there.